see, I see some chat in here. Okay, can you hear me now? Yeah, I wasn't talking yet. I was just getting ahead of the game, writing a few things on the chalkboard. Okay, let me get rid of this text. Okay, welcome back, everybody. And we're cutting our setup time period, so it's good. We're getting more and more efficient. So today we're going to keep talking about computational models, so ways you can organize your hardware. Next week, we might not quite finish computation models, but if we do, next week we'll be talking about kind of how efficient are FPGAs versus other devices. That's a broad question we can't fully answer. It depends on how you use them and what you're comparing to, but we can give some bounds and some analysis of that. That helps you pick, what kind of device should I use and what is their strengths and weaknesses. Reminder, Lab 1 is due Sunday, October 9th. How many people are working on it? I got to ask. Okay. How many people are done? For those of you who aren't, okay. Well, okay, one person's done anyway. How many people haven't started yet? You're just like, it's going to be super easy. Don't worry, I won't make it harder. So it's okay. If you say it's going to be super easy, it's just, you're just optimistic. It's not that hard, actually, I don't think. Okay, it's probably not a good idea to leave it to the last minute, though, because that's like super stressful if you're like, you have very little time, you have a licensing issue, which FPGA CAD tools love licensing issues. Just don't leave it to the end. A couple of readings that I'll post to the website for next week. These are related to this question of computational efficiency. The first one is a paper that I really like because they basically analyze what's the overhead of actually the processor model, right? Having instructions that you fetch and execute, it actually costs you a lot. They try to quantify how much that costs versus what if I just had hardware that did that exact thing, which is not very flexible, right? Processors are a lot more flexible, but let's get a bound on that. What if I built hardware that did exactly one thing versus I had a processor do that computation? And then the second paper is an analysis of essentially peak numbers. How many multipliers, how much memory bandwidth, et cetera, can you get out of GPUs, CPUs, FPGAs? Now, you're generally not going to achieve those peak numbers, so not the whole answer, but they are informative. They do kind of help you think about, well, what are some of the peaks, guaranteed not to exceed numbers across those devices. Okay, so Lab 1, again, you're free to write it in VHDL if you want, but most people will write it in Verilog. In case you're not that familiar with Verilog, here are a few references that I've already posted on the course webpage. So if you're kind of like, I actually don't feel confident in my digital design skills, I don't know anything about Verilog, in undergrad here, we use Verilog. In the textbook we use is Brown and Vranicek, which is a good book, actually written here at U of T, but this is a widely used textbook that's used a lot around the world. So that's if you just don't know how to write HDL. If you do know how to write HDL already, System Verilog is just, I don't know why they call it System Verilog. It's the next generation of Verilog, okay? So it's not, oh, I never want to use System Verilog, that sounds too complicated. It's just the next version. So you're either using the old version, you probably shouldn't, or using the new version. This is an overview of what's called the synthesizable subset, and there are 4 lectures here that are relevant. Lecture 1, to just change the number, you can see the next 3 lectures. It's basically, Verilog and VHDL were originally created as simulation languages. So they actually follow that communicating sequential processes, computational style that I talked about. And they were originally written to verify hardware. You could simulate any hardware you wanted. Only a subset of what you can write in them can actually be automatically synthesized or turned into hardware. And that subset was kind of a bit agreed upon by convention, right? Because it wasn't what the languages were originally designed to do. So these lectures cover like the most important part of System Verilog, in my opinion, which is the synthesizable subset, the stuff you can write that will actually turn into hardware. There's a lot of other stuff you can write that is useful for simulation in System Verilog. It's a much bigger language when you get into that part of it, but it's not as important because you probably mostly want to generate hardware. Okay, if you know HDL and you want to learn some best practices, Sutherland is kind of an expert on Verilog and System Verilog for design. So again, for creating hardware, not so much for writing simulation models to verify hardware. So if you want, you can go read his book about what are best practices, do's and don'ts. And then Cliff Cummings is a well-known Verilog trainer, and he's put a bunch of his papers that he's written on good versus bad Verilog practices that you can go read. So you don't have to read these. You can complete Lab 1 without reading these advanced texts. But if you just want to learn how to write better code, you can go read those. And if you already are comfortable with Verilog or System Verilog, then fine. If you're not, these lectures are probably the kind of a very succinct way to learn how to write synthesizable HDL. Okay, how many people here know Verilog? I guess from the course survey I did, a lot of people I think know Verilog. How many people know System Verilog? Okay, so reasonable subset, but not everybody. So I'm going to assume that wasn't just people getting exhausted putting their hands up, and there's a significant number of written Verilog, but not System Verilog. So, okay, everything you write in Verilog, is legal System Verilog. So it's not really a new language, just the next standard. It cleaned up some things. So here's a few suggestions of things that you should do in System Verilog differently than you used to do. You don't have to, right? It'll still compile if you don't follow this. But basically, because always blocks are basically just processes in a communicating sequential process model. And initially in Verilog, when they decided, okay, let's make this synthesizable, you just use an always block, whether it was supposed to be registered logic or combinational. And that actually can lead to a lot of subtle bugs. If you just don't write it quite the way the synthesis tool expects, you'll get something that is not registered logic when you wanted registered logic, not combinational when you wanted combinational. So System Verilog made two versions of the always block. Always comb basically is only for combinational logic. Always flip-flop is only for registered logic. So it kind of makes your code more explicit and allows it to do better error checking. If what you wrote inside that block isn't actually going to be registered logic, it'll say this doesn't really make sense. The other thing, okay, how many people in Verilog have been confused by what the heck is a wire and what is a reg? And why do they have both these things? I was confused by it. I thought it was bizarre. To think of why it's like that, you actually have to think about how a simulator works. Like, it's not really a design concept. It's kind of pieces of the original simulation design goals of Verilog showing through in the code you actually write. So it's not really desirable. And there's just rules you have to follow. Like, you don't actually get to choose. It's like, in this case, you must use wire. In this case, you must use reg. System Verilog, you can still use wire and reg. So if you're like, I memorized the rules, I love the rules, I'm going to use the rules to show I know them, you can keep using them. But if you never understood these rules, you found them annoying, you can just call everything logic, right? So all of your signals can just be logic, which is way smarter, because the fact that the rules give you no freedom, right? Like, in this case, you must use wire, in this case, you must use reg, is a good sign they shouldn't be in the language. You should just have one keyword, and the compiler should figure out what to do. So if you use logic, that's what happens. There's a little bit of style marks for Lab 1. Not very many, but a few. To get those style marks, well, this is always comb and always flip-flop, and using logic, in my opinion, is a bit better style. But we're not going to hammer you if you kind of don't use those. But it'll be a little better, so I'd suggest you move to those. And then you just want to follow good coding practices. So comment your code. Don't have magic numbers, so use enums or parameters to do things like name your states. When you have a shared operator version, the third version of the circuit you're writing, you're going to wind up with a finite state machine to control it. Much better to give the states names than just have like 0, 1, 0, 2, etc. Sorry, 1, 1, that kind of thing. Avoid duplicated code. So if you find you've written the same code several times, try to make a module that you can instantiate multiple times, or sometimes you can turn that into a generator or for loop. So generate can be a little tricky to use, so we're not going to be really pedantic about this, but look at your code and think, am I using hierarchy appropriately? Am I using these loop constructs to try to make my short code avoid duplication? And use meaningful names. So make your names very explicit. Okay, that is something for the end of the lecture if we get that far. Any questions on assignment 1 or anything else? Okay, yeah.
A brief question. I think in the first lecture, someone mentioned there was like an issue running one part of Lab 1 on the UG compute machines. Has that since been resolved?
It's been resolved. So I forget what the issue was now, actually. But yeah, we've basically set up the UG machines that they can do it all. And if you have trouble, there are a couple of Piazza posts on things that can go wrong and that you can fix. Oh yeah, actually I remember that one of the tools was crashing. We updated to the latest version of Quartus. I put in Piazza how to start it, and it doesn't crash. Okay? I think that's probably the one you're talking about.
That sounds right.
Okay, thanks. Let's see, so let's stop sending that to the projector. Okay, so last week we talked about a few different streaming models. So streaming is a very efficient, powerful model for hardware. And we went through kind of very more limited ones where all your data had to be at the same rate and you could never have essentially stalls or invalid data. Then we added valid tags, which made it a little more flexible. And then we actually added valid tags and back pressure, a ready signal. And we put FIFOs in to decouple things. So we went through a few different streaming models, and we also talked about you could mix and match them. If from this point to this point, that you will, if your inputs are valid, all the intermediate points will be valid and will never need to stall, then you can just use, regular registers with no back pressure. And then at the boundaries, if maybe my inputs at this point won't be ready, or I might not be able to produce an output for a while, then you could use back pressure and FIFOs. So you could combine them. Okay, so let's talk about streaming optimization. So we already talked about pipelining. If you write hardware in a streaming fashion, you can pipeline it, and that's really efficient in general and in FPGAs in particular because registers are so plentiful. So let's say I pipeline my HDL. So I put, actually I forgot to pipeline my HDL. Let's put a register there. Okay, now it is actually pipelined. So I put a register there, and let's say both these wires are coming from the output because that would make more sense. Okay. It can be hard to get registers in exactly the right spot. So is this good pipelining? So I went into my HDL. I originally just had registers of my input and registers of my output. Didn't run very fast. So I now put another set of registers, or another register in my design, in my Verilog. And so I get a register there. Do you like this pipelining or not? What do you think? Yeah. Okay. Yeah, so I think you're basically pointing out that it doesn't look very balanced, right? Like one of the things we said with pipelining is it's good to cut where you're not going to make many registers. Well, we didn't make many registers, so it's very good from that point of view. But from the point of view of, let's just do a simple delay model of, we say every one of these lookup tables plus the interconnect for its output takes 2 nanoseconds. And which might not be correct, but let's just go with that simple delay model. If we went with that simple delay model, we got 2 nanoseconds delay from this register to this register, and we got 6 nanoseconds from here to here. So the 6 nanoseconds dominates. That's the longer path. We can't clock this any faster than, well, we need 6 nanoseconds between clock edges. So you invert that, and you get something like, 167 megahertz, I think. I should have chosen a number that was easier to invert in my head, which is better than the 1/8 nanosecond clock frequency that we could have had before, but it didn't double. So it's not quite as good as we might have hoped. So you can say, well, you didn't do a very good job pipelining. Put your pipeline registers there. But that's iterative, right? Like a human's now got to try it, see where they go, move them. It also can be a bit tricky in your HDL. In your HDL, you don't actually have lookup tables. You have lines of code that are doing things. Maybe I was doing some and then some or some kind of decode. It might not be obvious. Well, what line of code do I change to move this register over here? Because you're not editing lookup tables. So does anybody know of an automatic optimization that could help us with this? This is something that CAD tools can help with. So do you know the name of the algorithm that can help you with this? So CAD tools can't actually pipeline your design automatically because they're changing the latency, and that might not be okay. They really, except with a bunch of restrictions on the design style. So there are certain, if you make enough restrictions on the design style, then a CAD tool could pipeline it. But in general design styles, a CAD tool can't actually change your pipelining. A human needs to go in and do it. However, CAD tools can move registers. Once you put them in, there is an automatic algorithm that can move them around. And when I say move them around, I don't mean move on the chip. I mean move where they are in your actual design net list. Like, so does anybody know what that algorithm is called? Yeah.
Maybe it sounds it's called retiming.
Yeah, so it's called retiming. So retiming, so how many people have heard of retiming? Do you know what retiming is? You've heard of it, because you just said the name. Anybody else heard of retiming? Okay, so at least 2 or 3 people. You guys might be the ones who work at Intel. Is that right? Do you all work? Intel has basically invested heavily in retiming. Okay, so retiming is nice, and it works well with pipelining. So again, in general, you have to put the pipeline registers in. There's no box you can tick to tell the CAD tool, well, like Lab 1, we gave you a functioning design, but we didn't pipeline it. There's no box in Cordis you can tick where you say, pipeline it for me, right? Which would be great. If you had that box, you'd be like, that was the easiest assignment ever, right? I just had to find this box. There is a box you can tick that says retime. Okay, so what does retiming do? Can you tell me what retiming does?
So it will try to move register around so that the path is moving back.
Yeah, so I'm just going to repeat that just so you can, so it's loud enough. It'll move registers around to balance path delays. So we didn't like this because our path delays are unbalanced. 2 nanoseconds on the input side of this register and 6 on the output. We have to take the worst case as our delay. We'd like to move this register over here to this spot. And if we could do that, we could actually get balanced path delays. Can I just move this register to this spot, like this one spot? Is that good? What do you think? No, you can't do that. It's basically you're moving a cut line. So I had a cut line here, and I could move the cut line to there. So what that means is if I move this register from here, I've got to move it to all the fan-outs. And that will preserve the latency of all the paths. And this is actually invisible to the end user. Basically, not only is your behavior at the inputs and outputs of this design unchanged, the latency is unchanged too. Everything will come out exactly on the same clock edge it used to. So that is something the CAD tool can do automatically because it cannot break your design. Okay, so retiming moves registers forward. So what I just talked about is the example I just gave you of moving registers from here to there, maybe I'll just draw it, would be forward retiming. I'd move the register further down my logic. Okay, so I can move it forward. I could also move it backward. Okay, and this is not moving it physically on the chip. It's actually at the logical level. It moves it across logic. And the reason it's doing it is to balance timing paths. Okay, so if I retime this, let's just draw this. Okay, so I have 2 registers going to L1. And I used to register that, but now I'm going to move this register basically up to its fan out. And I need to make a copy on each one of these because it's got to be a cut line again. So there was 1 register here, but because it goes 2 places, when I move it across these LUTs, I have to put 2 registers in. It's like a different cut line. Okay, so I'm going to go to L1. L1's going to go to L2 and L3. Okay, now I need a register. Okay, and it was 2 registers now, or it becomes 2 registers. L4. These are LUTs. So LUT 4, LUT 5, LUT 6, LUT 8, LUT 7. Sorry, I just renumbered that one as well. Okay, and then those go to registers. Okay, so if these are LUTs plus the routing of its output takes 2 nanoseconds, That's 2 nanoseconds, 4 nanoseconds to this register, 2 nanoseconds, 4 nanoseconds to that register. Okay, so for those timing paths, they're 4 nanoseconds long. And from this register, 2, 4, from this register, 2, 4. So these paths are also 4 nanoseconds long. Okay, so now my clock frequency, I can clock this as fast as 4 nanoseconds, which is 250 megahertz. So it's also a nicer number to invert, it's an extra bonus. So it's a significant speed up, okay? Okay, and in general, retiming, I mean, I just showed you forward retiming, but in general, it can also move things backwards. So for example, if I started out here, and I wanted, it's not actually useful, but let's say I wanted to retime these back, these two copies would actually merge into one register. So, and a retiming algorithm will evaluate both. Because in a more complicated circuit, you may find both of those things are beneficial. So every register, you know, some might get moved forward and duplicated, some might get moved backward and merged, and some it's going to find I can't move it, right? If I actually change the circuit to have that register there, and I didn't have a register here, and that was my input, this is what I created, a retimer cannot move this register back to here because it doesn't match. There's no other register here that it can kind of merge with it and keep all the latencies the same. It could take it and move it there. That'd be okay. But the only way I would get in this state is if that was my input, right? So if that's my input, then I can get here, but I could never get to that other state. Okay, so the nice thing about retiming is it can be done automatically by the CAD tool. It can also be done by hand. So you can apply this as kind of a mechanical transformation of essentially choosing where to move cut lines. But you can do it locally. If I move this register, I need to make 2 copies, right? If I move registers backwards, I need to make sure there's a copy on every one of the outputs. So you can use that to rewrite your HDL if you're finding that your timing paths are unbalanced. Although you don't have as fine-grained control. In your HDL, you don't quite know where the lookup tables are. You sort of have to guess. Okay, and the reason you can do this automatically in a CAD tool is it does not change the circuit behavior as you observe them at the IOs. Okay, so from the input-output, you know, here and here point of view, you cannot detect this has happened. The logic functions are the same, and even the cycle counts are the same. The latency is the same, so you can't detect it. Which is why a CAD tool can do it automatically, because if you can't detect it, the CAD tool says, well, how would you even know I did it, right? So, now this, okay, so in Quartus and Xilinx Vivado, these algorithms exist. Okay, they didn't exist. If you go back far enough in time, these ones are more advanced CAD algorithms. They weren't in the earliest versions of those tools, but they're in now. They went in, they were actually turned off by default for a long time, so you had to turn them on. In at least Quartus, for their latest devices, these are actually turned on automatically, or they're turned on by default, so you'd have to go in and turn them off if you don't want them. It's actually, as you're trying to optimize Lab 1, it's a good idea to go into the settings and see, is retiming on? Because if it's not on, you can just turn it on, and it should get you some more gains. Why do you think it's possible to turn this on and off? Like, if it's a good thing, why do they even have a control? And for many years, the control was off by default. Now, basically, deep pipelining and getting your pipeline registers in the right spot is getting more and more important. And you'll see some architectural reasons for that, so they've turned it on by default. But why do you think they even have a control? Because if it's always good, why don't you just always do it? What do you think? If you can't observe it from the outside world, why even have a control to turn it on and off? Okay, so it could be like, well, there's CPU time, or maybe sometimes the algorithm makes sense, and those would be reasonable reasons, but there's a more fundamental reason than that too. Even if your CAD algorithm was perfect, it was always fast and it never did the wrong thing, like it never made things worse. And sometimes retiming can make, it usually doesn't, but because it's sometimes guessing the delays earlier, sometimes it can make mistakes. But there's a more fundamental reason that you don't always want this on. So what do you think? Any ideas? Yeah. Could you say it louder? I couldn't quite hear it. So you think it might hurt your propagation delay? That's essentially the algorithm screwing up, right? So I mean, I'm showing you one here with just two sets of timing paths, and in a bigger circuit, yeah, there'd be lots of timing paths. A retiming algorithm is watching the longest paths and trying to optimize them. So if it's got a whole bunch of paths, it's focusing on the longest ones. As I said, they do have delay estimates because sometimes usually the retiming algorithm is running before the design implementation is complete, so it can make mistakes. So that's one reason. But even if your algorithm was perfect, there's a reason you want to turn it off. What do you think?
Maybe it's possible for retime to take far more resources if it keeps pushing it down like a lot of fan drills.
That's actually a good idea. So I didn't think of that, but you're right. That could happen. It is a resource trade-off, so you might wind up with, I don't actually like the resource trade-off. Retiming usually doesn't increase register usage too much because it pushes some things down, but it can push some things backwards. But you're right, it could. So in certain structures, so that's a good point. Okay. Any other ideas? So, yeah.
Maybe like it's not really the same as what you did now.
Yeah. So from the input-output point of view, you can't tell that retiming's been done. Okay. So if your circuit worked and you didn't have to ever do any verification or debugging inside of it, that's good enough. But the odds of something work when you first write it are approximately 0, right? Like they're epsilon. But like when you write something and the first time you simulate it or compile it or test it, it works, this was a lucky day. You should probably go buy a lottery ticket because you're having a blessed day. So usually things are broken. And what retiming does do is if you look inside the circuit, these registers are different. So this register in your HDL will have a name. It has a function that you understand. You know what this thing is doing. Maybe this is a counter, for example, or maybe it's an enable signal under some condition. But you actually know what this should be. If you bring up waveforms, you can actually say, oh, wait a sec, okay, for these inputs, you know, this register should have been this value, and it's not that value, so I got a bug, so I got to go and look at it. Once you move this register to this new spot, it's much harder for you to reason about it. It's no longer a register that's in your HDL. It's not, you know, registering some signal that you wrote and understand. It's registering something, you know, something related to that, but you don't quite understand what that is. So it's much harder to debug. So it's pretty common to turn off retiming if you're actually trying to debug this. If you're debugging your RTL before you put it in the FPGA, that's fine. No retiming has happened. You're just running model sim on the functional model. If you put this in the chip and things are going wrong, there are tools that the FPGA vendors have where you can actually basically observe the registers and bring data out from the running system. Okay? And sometimes you have to use those tools to actually debug the hardware because you're getting unusual cases that you missed when you were simulating the design that are showing up as bugs in the hardware. If you've used retiming, it's going to be a lot harder for you to interpret, like, what are these registers? These registers are not things that I actually put in my RTL. Does that make sense? But so most debugging occurs when you're at the functional level, when you're debugging your RTL, and this retiming doesn't happen for that. You know, this is when it's actually implemented on the chip. So you can leave retiming on certainly for the final compiles when everything's working. You can leave, maybe you'll never have a problem in hardware that didn't show up in simulation, in which case it's fine. If you have a problem in hardware and using those pull back by state debugging tools, you usually want to turn off retiming so that you can understand what's going on. Which also has some trade-offs. You know, if it was a sort of a very subtle bug related to timing, then it's actually possible it goes away when you turn off retiming. But it is going to be a lot harder to interpret these registers when you read them back for hardware if you had retiming Okay, so that's retiming. Another optimization. Oh, actually, one other question. So I said you could retime by hand. It's like a mechanical procedure that you can apply in your RTL, or the CAD tools can do it automatically. Should you ever do it by hand? Or like, if the CAD tools can do it, is this just pointless to ever do by hand? What do you think? It's probably a hard question to answer, unless you've had a lot of experience with the CAD tools. That also means like any guess is fine, right? It's like a yes. If you're looking for like what question could I answer? It's like a yes/no question with no obvious answer. You just take a random guess. Amin, what do you think? So is there any reason to ever, so I'm going to put Amin on the spot. So any reason to ever retime by hand? Or is that like a lost skill now that the CAD tools can do it? Not sure? Okay. So it's still useful to be able to retime by hand at the RTL level because you're tending to do bigger scale retiming. You know, you don't even know exactly where the LETs are. You just look at the timing report and you see this path is long, this path is short. I'll try, could I move this register to a different spot in my RTL? The reason that's useful is these CAD algorithms, they use delay estimates and they actually run at multiple stages in the CAD flow, certainly in Quartus. Early on, before they've done much of the design implementation, so you're doing what's called synthesis, where you're just deciding what the logic is based on the Verilog you wrote, they can move the registers quite a bit, but they have pretty poor delay estimates. So delay estimates can be wrong. Later on, when they actually get into near the end of placement and routing, so they kind of know the delays pretty well at this point, but it's harder to actually move registers around because you might be duplicating them and you got to reinsert that into the placement, which is basically done. So you have more information about what to do, but it's harder to reinsert. That means the CAD tools are not perfect at this at all. Okay, early on they're guessing. Later on in the compile, they can fine tune, but it's hard to integrate the changes. If you give them a better starting point, your results will generally be more robust and usually better, right? Like you've helped the CAD tool by giving it a better starting point because they're not perfect at this kind of retiming. So it is still a useful thing to do. Does that make sense? Okay, so that was one optimization that we can do. Okay, another optimization that comes up sometimes is really fast blocks. Okay, so let's say that this is an IP block, so something you didn't design, and it turns out that it's just really fast. It's kind of over-engineered for one of your data streams. Okay, so I've got an IP block. This might be hard for you to guess. So, you know, you're going to have some throughput in this IP block that you're not using if you just send one stream through it. So you could actually time domain multiplex it. So you can time domain multiplex it across multiple streams. Okay, so time domain multiplexing is like another class of optimizations. And the good way to do this is it's just like we did with valid bits and kind of ready bits where your control is distributed. You're kind of tagging your data. We've already tagged data with like valid if we needed that. And we can have ready to say whether we should back pressure or not. You can add one more thing in this case, which is you can tag your data with the stream ID. Okay, so if I do that, I could actually send multiple streams of data into this IP block, and its output's going to be all interleaved, but I can look at the stream IDs to take it apart again. Okay, so let's say I have some function I wrote, and I'm not all that good, so it runs not that fast, runs at 200 megahertz, produces an output every cycle. I'm going to put that into a FIFO. Okay, because I'm using the streaming model where I have back pressure and FIFOs. I use an IP block, and let's say IP block's pretty expensive. So maybe it's an FFT. Pretty big IP block, heavily optimized by somebody. I bought the IP block from them, or I got it from Intel or Xilinx. And this is really well designed, runs at 400 megahertz. So this was done by a better designer than me. Okay, and then it goes out and it's going to go into a FIFO. Okay, so for my stream A. So I'm basically sending a stream of data in. This will work, right? I've got valid bits on here. So this is going to stall every second cycle because it's processing faster than I can feed it data. But if I have another set of work to do, so another stream of data. Again, FPGAs are often used in signal processing and communications. So I might have multiple sets of data to send through the router or multiple wireless communication channels that are active. So I have another stream that I could work with, stream B. So I put that through another function. Maybe it's different, maybe it's the same, but we'll call that unit FB. It also runs at 200 megahertz. And now basically I've matched the throughput. Okay, I put another FIFO on the output of this. So because these units are tagging, they're inserting basically stream IDs, H just passes those through. Doesn't really need to do anything with the stream ID. But on the output, I can look at those stream IDs and basically take them apart again. Put stream A into FIFO A, stream B into FIFO B, and keep going. If this was a small unit, this probably isn't worthwhile. I can just make 2 copies of it, and the fact that it's extra fast, I just don't care. But if it's a big, expensive unit, I'd really rather not put 2 copies in when one of them could handle 2 streams if I had a bunch of streams. So yeah, so it's another approach you can use for kind of rate matching when you've got some really good hardware that's expensive. All right, so let's see. Okay, so that TDM technique, time-domain multiplexing that we just talked about, is a general technique that we can use in a bunch of places. So we talked about how you can't pipeline loops, which is a pain, right? They limit your clock frequency a lot of the time. But we can time-domain multiplex them. Okay, so let's take my little loop circuit from last week. Okay, and okay, so I had last week I put an X in here and I got a Y out there, right? 2 streams of data. And we couldn't pipeline the loop. So whatever the delay of this was, that was it. Okay, I'm gonna put a register here. So whatever the delay from that register to that register was, we couldn't do any better. That was gonna limit our clock frequency. So a way that I can put a register in here, so I'm gonna stick one in there. Okay, which I can't just do that by itself. I stick that in by itself, and I've changed my computation. My Y of I's are not computed now based on the previous X. They're going to be computed based on an X 2 cycles ago, which is wrong. What I can do, though, is I can put a multiplexer here. And on one input, I put X of I. Or X1 of I, so assert one stream of data. And on the other input, I put X2 of I, so a different stream of data. And I'm going to flip between them every, I'll say clock. The idea is every cycle I flip between them, okay? So I send one piece of data from stream 1 in. The next cycle, I send one piece of data from stream 2. Cycle after that, I go back and I send the next piece of data from stream 1, and I keep repeating that forever. So if you work through, what does that mean? By putting this extra register in, I'm actually computing Y as a function of my prior output, or my current output, and something that happened 2 cycles ago. But the input I got 2 cycles ago, because I'm now sending in one stream 1 cycle and the other stream the second cycle, what I had 2 cycles ago is actually the previous value in that stream. Okay? Does that make sense? So the combination of putting this register in and interleaving at the input between two different streams makes my latencies match up again. So I now get two output streams. I get y1 of I, which is equal to f2 of f1 of x1 of I, and y1 of I minus 1. Okay? Which is what, if I go, remember the original circuit with no register there, and I probably shouldn't put this register here either. I think this register is going to mess up my example, so I'm just going to remove that from there. So, so that means the registers are like back here somewhere. Without this new register and without this multiplexing, this is the function I would be computing. The current x and the previous y. And when I put both the register in and this multiplexer in, that's what I get for stream 1. And it's also what I get for stream 2. So y2 of I, second stream, is equal to f2 of f1 of x2 of I. Whoops, forgot the y. And y of I minus 1. Okay, so does that make sense? So it's a way you can get, it only helps you if you have more than one stream of data. Like if you only had one stream of data, this doesn't really do anything useful for you. Because the second stream would just, say, be putting in a bunch of zeros. So that's kind of useless. But if I did have two streams of data, it means I could actually use one copy of this unit, pipeline it, clock it faster, and maintain approximately the same throughput. Does that make sense? Okay, so this actually technique this technique of time domain multiplexing to allow deeper pipelining has a name. Okay, so it's called C-slow retiming. Okay, and it's a mechanical, you can apply it as a mechanical procedure. Okay, so you make C copies of each register. Okay. Maybe I should actually draw. In my notes, I drew this. Maybe this is actually helpful to draw. What comes out here is y1 of 0, then y2 of 0, then y1 of 1, and so on. Okay, so what comes out is basically like an interleaved data stream. Okay, so C-slow retiming, you make C copies of each register. And you make them in series. So let's take this example. I didn't actually put, yeah, so if I take this example, first step in C-slow retiming would be F1, F2, got a register, and I had, came out to Y, and it had a loop. Okay, and this was my X. Okay, so that's my original circuit. C-slow retiming says make C copies. So you choose what C is. C is how many copies of each register you're going to make. So I'm going to choose C equals 2. Whatever I choose C to be, that's how many streams I'm trying to multiplex. So I'm trying to multiplex 2 streams. I'm going to say C equals 2. So I need to make 2 copies of this register. So what do you think? Should I put them in series or in parallel? What makes sense for this? Yeah, so series is what makes sense. So I take this register and I basically make 2 copies of it. Okay, so now there's 2 registers. So that's my first step. If I stop here, I broke the circuit, okay, because I can't do that. I can't just change the pipelining of this. So my second step is I now need to put in this mux, and I need to send in C streams. Okay, so I'm now going to interleave cycle by cycle between the stream X1 and the stream X2. That now fixed my circuit. It's going to produce this output of interleaved data. Okay, so send in C interleaved input streams. Okay, so my design's correct again. Doesn't seem really useful though. So far it clocks at the same rate as it used to, and I just basically said instead of putting in one stream and getting a result out every cycle, I put in 2 streams and get 1 for each stream every 2 cycles. So I get 1 for one stream, 1 cycle, 1 for the other, the next cycle. It doesn't seem useful. Can't clock it any faster yet. But as the name implies, the third step is just retime. So retime to distribute the registers. Okay, so these 2 registers are not useful from a timing point of view because they're right beside each other. But now that I've got 2 registers in this loop, I can retime them. So I can basically say, well, I can take this register and I could move it into the fan out, like into some downstream logic. So I could say, let's move it here. Or equivalently, I could have taken this one and said, let's move it to its fan in. Either way, I can basically say, let's get rid of that. Let's move that register. It's no longer there. And now it's here. That was just retiming. Did not change my input-output behavior of the circuit. But now I've nicely distributed my registers, and I can clock this probably about twice as fast. So it's a mechanical procedure to go from some hardware, often with a loop in it, that's why you're doing this, to that same hardware that's interleaving between C streams and is pipelined C times more deeply, and then you've moved around the registers with retiming to get a clock frequency that's around C times faster. Okay, so what's the game? So the registers are pretty cheap in an FPGA. So I did add some registers, but that's pretty cheap. Add a little bit of muxing, but probably not much. So I haven't added very much area. Can I clock this faster? Assuming that I really retimed nicely, how much faster can I clock? What do you think? There's only one constant here, so there's not that many guesses that you could have. So maybe this is so easy, you're like, there's no honor in this. You just put the class out of its misery. Say, how much faster can I clock this? What do you think? Yeah, so you can clock this. If everything works out perfectly, you can clock it about C times faster. So that doesn't get you one stream through faster because you need C clocks. Like you have C clocks between data elements of one stream, but you do get C of these streams through at once. So it doesn't increase the throughput of any one stream, but under ideal circumstances, you get C times the total throughput. So if you had a whole bunch of streams to send in, this is good. So you get C streams through the same hardware. At the same rate. Let's see. Okay. Any questions on that? Or is it all pretty clear? Yeah. TDM stands for time-domain multiplexing. Is that what you're asking? Just like, what does it stand for? And the time-domain multiplexing is, we call it that because we're essentially sending multiple streams through the same hardware. So it's like we're splitting usage of the hardware over time. Because our whole goal in doing this is to pipeline it, we really have intermediate results from multiple streams kind of in the hardware all at the same time. But from the output perspective, we kind of get a bunch of outputs from different streams interleaved cycle by cycle, okay? And it's a way that, yeah, we can now pipeline loops, okay? Doesn't help us with one stream, but if we had a whole bunch, it does help us get several streams through the same hardware in less time. Does that make sense? Okay, so let's see. Let me... a visiting professor's visiting my group from Imperial College, so when he saw me going off to lecture with this bucket of rags and water and so on, he was curious about what lectures are like in Canada. So, because definitely does look like I'm doing a little custodial moonlighting. So. Okay, so that's it for the streaming models. We've talked about, and we've talked about them more than most other programming models because they're important. Efficient hardware, widely used. Okay, but they're not everything. So another one is finite state machine with data. Okay, so FSMD. So this is like, it's a bit like a microprocessor. So, and this is actually the programming model. Okay, so in lab 1, we give you a basic stream circuit, just so you can learn Quartus and see how it functions. And then you're asked to optimize it. So you should go in and you should pipeline it, make it faster. And then we ask you to make what we call a shared operator version. So a shared operator version is like a finite state machine with data. Okay? So let me show you what that looks like. So it's like it is custom hardware, but it has some similarities to a processor. So it's like a custom, special purpose, basically, hardwired microprocessor. So it doesn't have an instruction stream. Instead, it's got a finite state machine. And that finite state machine is generating a bunch of outputs. And those outputs are controlling a data path. So instead of controlling a data path to an instruction stream, you're controlling it from a finite state machine. So let's say I've got some computation I want to do, like the quadratic equation that we looked at in the first lecture. So I needed a multiplier, I needed an adder, because I had multiplies and adds. I need to select what am I doing. I need to be able to store my outputs. So I've got some bank of registers. Okay, so that's a register bank. And I'm going to complete this more complicated computations using temporary values that I store in the register file and multiple passes through the data path. So just like a processor. So I need to be able to read things out of this, send them up here to my data path. Now I need to have some way to get new inputs into this data path too. So let's say this will be input 2, goes in there. So I got a mux that controls whether I take a new input in or take something out of the register file. Here I've got another mux, so I could take a different input in one, or I could take something out of my register file. And if I draw this arrow, okay, so this data path is a lot like a processor data path. I got a multiplier, an adder, I pick which one, I can store things in the register file, I can take things out of the register file, I can also send new inputs in 1 or in 2 into this data path, but I need to control it. And I control it with outputs from the finite state machine. Okay, so I need to control these muxes. So I got some output from the finite state machine to control them. I need to control this mux. And I need to control this register file. Which register am I trying to control? Does it make sense? Now in a processor, you generally make this data path pretty general. It can do anything. Here you make the data path only have the operations that you need. So it's kind of stripped down. Probably make the register file only as big as you needed it. So you make however many registers you need for your temporaries and so on. That's all the ones that you make. And you have multiplexers to select them. You have a finite state machine that walks through and just controls what is the state of every mux. And this is good for repetitive calculations. Like this finite state machine is just going to do the same thing forever, right? So this is not good if you had some huge long list of computations or it varied over time, et cetera, then an instruction stream is better. But let's say I've just got like that quadratic equation. I'm just doing that forever. So I'm going through the same few operations over and over again. Well, a finite state machine can do that. And it can do it essentially with less area than an instruction set if what you're trying to do is pretty repetitive, not that much. Okay, so what's this good for? So it can be good for, it can be suitable, well, what do you think? Compared to streaming hardware, we looked at the full streaming version of something like this. Do you think it's going to be smaller or bigger? Let's say if I was computing the quadratic equation. So it's kind of like what we looked at in the first lecture, where we had the quadratic equation computed by a processor versus computed by streaming hardware. Do you think it's going to be smaller or bigger? Yeah, smaller. It reuses the data. Finite state machine's not that big. As long as the muxes aren't too big, you know, if I had a huge number of registers here and the muxes start getting huge, well, then this might become inefficient. But if I don't have that many temporary values, so muxes are pretty small, then this is typically going to be less area than a fully streaming version because we're reusing hardware. Okay? And I guess I'll let you think about whether, you know, do you think, well, maybe we just talk about this. Do you think it's going to have the same throughput as streaming hardware or not? Yeah, I see you're shaking your head. So you think not? Yeah, why do you, and it generally won't, right? So why do you think it won't have the same throughput? Yeah, yeah. So basically it's sequential. So, but because it's sequential, it's unlikely to be as fast as a well-optimized streaming implementation, at least. But it is likely to be smaller. So one of the things you're asked to do in Lab 1 is, well, often in a chip you have multiple choices. You're going to you can put as much stuff in as you want until the chip is full. So if this is smaller, you should be able to fit more of them in. On the other hand, it's probably not going to get as much work done per unit time. What's going to get you more throughput, right? Should you just have a higher number of replications of this? Or is the streaming hardware, despite its larger size, going to more than make up for it by being so efficient in throughput? So those are some of the calculations you're going to do. And you're also going to look at energy efficiency, which is a little more subtle still. And I'll leave that for you guys to think about. And you don't just have to think about it. Like the tools will actually tell you which one is more energy efficient. Then you just have to kind of think of why might that be. Okay, sorry. So this is a good choice, just like microprocessors, suitable for kind of rare or limited parallelism operations. Okay, it's going to be pretty space efficient, but it's going to be lower throughput. Okay, so that was a finite state machine controlling a data path. Let's see. Next one is VLIW. So what does VLIW stand for? Does anybody, some of you have probably seen this acronym before. Has anybody seen it? Yeah, very long instruction word. So it's just a form of processor. And so it basically means you're going to control your data path with instructions. And in very long instruction word processors, it's okay if the instruction has a lot of bits. So you can imagine just taking this data path, where we've kind of just exposed all the control of the data path, and if instead of controlling it with a finite state machine, we just said, well, that's just directly controlled by the instruction stream, that's a form of VLIW. So it's not the only one, but that basically allows you to transform this to a custom processor model, where you actually have an instruction stream. Okay, so it's basically just control a data path with instructions. Okay, and yeah, if you make that data path kind of complicated and you expose all of the control of it, your instruction word will tend to get kind of long or wide. If I'm doing just a few things, then a finite state machine is, it's not too hard to code, it's pretty efficient. If this data path gets kind of big and my sequence of operations gets long, then the finite state machine might start getting kind of hairy. And at that point, there's often a break point where it just gets not only easier to code, but even more efficient to, instead of building a huge finite state machine, just actually thinking of it as instructions and storing the instructions. Okay, so it may be easier. It's not just easier, it can also be more efficient, so it can actually be better as well for wide and complex data paths. Okay, and let's see. See how many boards I have free here. SIMD. Okay, so SIMD is another acronym from computer architecture. What does SIMD stand for? Yeah, single instruction, multiple data. So it's kind of related to VLIW, but it's not exactly the same. So it means many parallel execution units which are all the same. And they all share control. Okay, so that control could be instructions, like we had here, or it could be a finite state machine, like we had there. Okay, and the reason to do this, well, it's just to amortize your control. It's smaller. Well, it's smaller than having a whole bunch of independently controlled function units. So if it turns out that you tend to do the same thing on a lot of data, this amortizes your control. And your control is kind of overhead, right? It's not actually doing computations for you. It's just organizing the computation. So let's see what this looks like. So here's my control logic. Could be instructions, could be a finite state machine. And I've got some functional unit. I've got some memory feeding it. So I could just control these with one instruction stream or one FSM. But if I figure out, you know, my computation has a lot of parallelisms. It's working a lot of vectors, for example. And we tend to do the same thing to the first vector element as the second vector element as the third vector element. Then I could say, well, let's make a few of these compute units. Say 3. Say I figure out that I tend to be doing stuff on 3-dimensional coordinate data. So I tend to do the same thing on 3, like the x, y, and z component of a vector over and over again. So I can say, well, let's just make these run in lockstep. So my control is just going to run all of them. Okay? So that can make you more efficient by amortizing the control. It can also sometimes help you think about it. So it can be easier to organize. So it's easier to organize control. An example from one of my students from some years ago. He was doing a matrix factorization engine. So there's something called LU decomposition. And that's where you take a matrix and you factor it into the product of two matrices. One is lower triangular, one is upper triangular. After you do that, you can easily solve equations like AX equals B for that matrix. but it's computationally expensive to do that factorization. So there's LU decomposition engine. And it's operating on rows and columns of a matrix. So there's kind of obvious data parallelism there. It's actually not only more efficient to use SIMD on this, so that instead of operating on, take this element and subtract it from that element, we say take this piece of a row and subtract it from this piece of a row. So that is more efficient because we amortize the control over a bunch of different function units. And we basically built 144 of these processing elements that basically could do some operations of, subtract this from that and a few other things. So that was more efficient because we only needed one copy of the control logic instead of 144. Sometimes it resulted if the matrix wasn't divisible by 144 columns, you're going to wind up with some inefficiency, so you lose something. It was also easier to think about, right? By doing it this way, having all the processing elements working in lockstep, just on different elements in a row, it was a lot easier to think about what that means. Some other ways of organizing the hardware might have been more difficult to control. Okay, so it's 144 PEs, and they were operating in lockstep. Okay, so SIMD is used by processors and GPUs as well, so this is a general hardware concept, but it's not limited to them. You can use it when you're designing hardware by just realizing I'm working on a lot of parallel data, it's all in lockstep, I'll make my control do that. Okay, so I think, well, any questions on that? Okay, so yeah, go ahead. What is the last?
The lockstep.
Oh, the lockstep means I've got 144 of these processing elements, and I've only got one copy of the code of the control. So they're fundamentally operating in lockstep. They're all doing the same thing. Like each of them is loading, say, a value from this row. It's just every PE gets a different one. So PE1 might be getting that value, PE2 might be getting that value, but they've both been executing load your data, right? Starting at this point, and everybody knows, well, I'm offset by a certain amount from that point. And then they might all take it and multiply it by the corresponding value here. But they're all operating, they're all doing the same thing. Does that make sense? They just have different data. Does it make sense? So that's what I mean by operating in lockstep. And it's kind of fundamental they're operating in lockstep. Like they have to. There's one control circuit controlling them all. So this is like 144 students sharing like one head, okay? Might be a disturbing image, right? But they would all be walking down the hallway at the exact same time. Sound good? Sorry, what's that? LU is just, this is actually the application. So LU is lower upper. So it's a way that you can factor a matrix of the product of two matrices. So that was just an example application. So you can just take that as application working on matrices, and it turns out we need to do a lot of it. It's a complicated, well, it's computationally intense, and it involves a lot of take this whole row, multiply it by some element, subtract it from this row, then this row, then this row, then this row. So it kind of has abundant parallelism that you can express as SIMD. Does that make sense? And actually a lot of linear algebra operations can be expressed as SIMD pretty well. Which is part of why the GPU program model is effectively, well, they don't call it SIMD, but it's either is SIMD or extremely close to SIMD, okay? Does that make sense? Okay, so let's take a break until 5:30, and we'll come back here. We good? So yeah, I was checking the chat. So for those online, Zoom does a lot of video compression. So don't look. The reason we have a YouTube live stream is the chalkboard is not going to be visible in Zoom. So yeah, go to the. If you're not looking at the live stream, look at the live stream because it's way higher resolution. Zoom is fine when you're sharing slides because it shares them at full resolution, but its video is actually pretty low res. Okay, so my next programming model is a soft processor. What is a soft processor? Does anybody know what that means? Nobody's heard of it? People at Intel, I know there are a few people from Intel and AMD in here. I know you guys have heard of it. So you're just being shy. So what do you think? What is a soft processor? Yeah, what do you think? So you're saying a processor with some customizations. You can customize it, but you don't actually have to. So, so what makes it? Where does the word soft come from? I guess not in a historical sense. That would be too broad a linguistic question. But in this context, why do we call it soft? Yeah, so in FPGAs we use the term soft just to mean built out of the fabric. Like we take the reprogrammable resources like lookup tables and routing and we make something out of them. And if we did that, we call it soft. And if you can point at some silicon on the chip that only does this thing, then we call it hard. So a soft processor means I didn't go and buy an x86 processor from Intel or an ARM processor from somebody. I basically just programmed part of the FPGA to actually be a processor. And now it's a processor and I can program it with an instruction stream and do anything I want with it. So there are, basically every major FPGA vendor has its own soft processor, or they're using RISC-V. Some of them now have just chosen, okay, we'll use RISC-V because it's open and that's a competitive advantage. So Intel has Neos, Xilinx has Microblaze, and Microchip has decided we're going to use RISC-V because we'll go with the open one. And they didn't make their own soft processor, which they've now kind of is smart. If you didn't make your own and you're kind of later to the party, you go, I'm going to go with the open standard, and it's going to make Intel and AMD nervous. So all of them have these soft processors that are like Verilog, and you can basically just program it into the chip, and then you have a processor. Why would I do this? Like, why is this a useful? What is this useful for? What do you think? Any ideas? Is it useful? Well, so there are papers where people say, I bought a big FPGA, and then I programmed 1,000 soft processors into it that I then programmed to work together in some multi-threaded way, right? They divided up an application and started working on it. So that's one way you can use them. Do you think that's the best way to use them? Is that the typical way to use them? Or what would you use these for? You could also say, I'll just never use that. I only design hardware. That's an abomination, right? So, which is fine. You could do that. But these do get used a lot. So what do you think? Do you have any idea? Or are we just stretching? Okay, I don't want to put you in the spot. I don't want to. Stretching is important. I don't want to put you on the spot just because you stretched. So, okay, so I'm going to put Amin on the spot. Now he wishes he stretched. Amin, what would you use the soft processor for?
I think if you have some kind of new idea for a processor, it's going to be very expensive because usually.
So that's one. If you were a processor researcher, and you're right. But let's say I'm just a user. I'm going to use Neos or Microblaze or RISC-V. So there's no like I'm developing a new thing. I'm just basically saying I want to put that in the chip. And the IP core for that is in, depending on which FPGA I'm using, it'll have one or the other IP core. I just plunk it down. So why would I do that rather than? Yeah, so that's a good answer. So okay, the soft processor you can change, and so you could augment it. That's what we're going to do next. Okay, so if you're just going to use a soft processor. And you're not going to change it at all. It's just going to be like a conventional, classic processor implemented on the FPGA. As I said, there are people who publish papers where they just fill an FPGA up with these and try to compute things in parallel. I don't think that's it's not a common thing to do. It's probably not the best use of an FPGA. But what it is useful for is it's useful for housekeeping. So a modern FPGA has, remember, logic elements is basically like a lookup table and a register. Okay, so it's pretty small. And depending on what kind of, how big an FPGA you're buying, you're probably buying between 100,000 and 10 million of these logic elements. A soft processor, it's not a super high performance processor. They usually run at 300 or 400 megahertz. They execute, they're pipelined, but they're not super scalar or anything. They execute one instruction each cycle, you know, if they're not stalling. Whereas you buy like a high-end x86 processor, and they can complete, you know, maybe 4 instructions per cycle, and they clock at 3 or 4 gigahertz. So this is going to be much slower. You know, 400 megahertz. Best thing it's going to do is 1 completed instruction per cycle. But they're also not very big. So there are different flavors of them. So the cheapest, slowest ones might take 500 LEs. A big, somewhat faster, more pipelined one may take a couple thousand. Okay, if you have 10 million LEs, that's not a lot. Even if you have 100,000, it's not a huge number. So it's not very big, but it's not that fast. So it's useful for housekeeping. Like you often just have some initialization, some setup, some error conditions, and you could write finite state machines or something to try to do that, but that can be a pain. And you're just not, it doesn't have to be very fast, and these soft processors don't take that much room. So you can also use it, this is kind of what Amin is saying as well. So you can use it for hardware control. Okay, so housekeeping is kind of setup, error conditions, rare things. Hardware control is kind of getting into the augmented, right? Or maybe we can write to some registers in the hardware and have it control them that way. You probably, even though there are those papers where they make many, many soft processors working together, that's probably not the best use of them. So probably not for heavy lifting. And the reason why is you've got 2 levels of programmability, okay? Okay, so your first level is the fact that you're using the fabric of the FPGA, right? You can rewire things, you can change the lookup tables. That's actually pretty expensive compared to just making the hardware. And then you've got a processor, and a processor interprets an instruction stream and then it uses that to control some muxes and ALUs and et cetera. And that's also actually quite expensive. So there's actually essentially a large efficiency loss with each of these levels of programmability, and you've kind of stacked 2 of them on top of each other. Okay, it's an unanswerable question, but we'll go through some papers next week and that kind of try to give some bounds on how costly is this programmability. What do you think it is? Like 1.5x in terms of like the amount of throughput I can get per unit of silicon, right? So let's kind of multiply the area times the clock period. That kind of tells me that's the opposite of how much throughput I can get through the silicon, right? If I'm smaller, I can make more copies. If I can run faster, I get more done. How much do you think you lose with each of these levels of programmability? So 1.5x, 2x, 10x, 100x, million x. Just take a shot, right? It's like, you could guess less than 1. You could say, no, programmability makes me more efficient, right? Just to give you all the options. 10x? Yeah, 10x actually is roughly my guess too. Okay, if you were to pick like a round number, 10x per level. So we're going to see this in a couple of the papers we're looking at over the next week or 2. But a pretty reasonable guesstimate for, there's a wide range here depending on what you're doing, but yeah, the efficiency loss is large. It's on the order of a level, it's around an order of magnitude. That's a reasonable estimate. So yeah, doing that twice is kind of painful. If you buy a hard processor, like if you go buy an off-the-shelf ARM processor or x86 processor, you pay for 1 level of programmability. If you buy an FPGA and put streaming hardware in it, you pay for 1 level of programmability. And you get a lot for that. You know, you paid a lot, maybe 10x efficiency versus dedicated gates, but you also saved, you know, maybe $100 million to go make that custom chip. So, you know, there was a big payoff. This soft processor, you're getting a second level. So instead of 10x cost, you're getting like 100x cost. And what you gain is convenience. I didn't have to program hardware in, I just program a soft processor. So that's worth something. And if it's just a little piece of your design, you don't need much performance, it's a great choice. But if it's the heart of your design, you're sticking 1,000 or 10,000 soft processors in and filling a big expensive chip, in my opinion, that's not extremely logical, but there are people who do that. So, okay, so that was soft processors and just kind of vanilla soft processors. Okay, but it gets more interesting when we start talking about augmented processors. So people do use just completely vanilla, RISC-V, Neos, microblaze processors for housekeeping. But the nice thing about a soft processor is you can change it. So there's two basic ways that people change them. First one is called custom instructions. Okay, so most of these soft processors, there are really cheap ones, there are somewhat more expensive ones, but the kind of ones that are in the middle, and when I say expensive, I mean like how much logic they take. So the one I'm about to show you would take maybe 1,000 or 1,500 logic elements. They use a 5-stage classic pipeline. Okay, so who knows what I mean by a kind of 5-stage pipeline? You guys all remember that from computer architecture? I think you do. Some of you shaking your head. Well, it's not hard to explain, and it doesn't matter too much. But basically, a very not too big, but reasonably fast processor design is to use a 5-stage pipeline to process an instruction. And the control logic to design such a processor is not that complicated. So this is much, much simpler than if you go buy some high-end x86 or ARM processor. So it's not nearly as high performance as that, but it's not bad, and it's quite area efficient. Okay, so this is the classic 5-stage pipeline. Fetch the instruction, decode what it means, use that to control your ALU, read or write from memory if you had to, and then write the result back to the register file. And decode usually also read the register file. Okay, so what a custom instruction does is right after decode, where I've figured out what the instruction means and I've read the operands from the register file, I basically can say if it's a certain reserved opcode, you basically make some opcodes that the processor doesn't do anything with. So they have no meaning to the basic processor. And you can use those opcodes. And when one of those opcodes is detected, it just broadcasts it to some custom hardware that you wrote. And that custom hardware executes in the same clock period that the ALU operation or execute operation would normally happen in the processor. Okay, so this could be anything, right? You just wrote a block of hardware to do whatever you want. It's not normally going to be like things like add or multiply because the ALU can already do that. So it's something else that you thought was useful. What is this useful for? Well, what do you think this is useful for? So if you can do this, right? You can go into Quartus, you can take the Neos processor, and you could go write custom instructions for it. So there are tools inside Quartus to go do that. I don't want to set up the license for you, but if you want to explore them, go ahead. What do you think this is good for? Any ideas? That's a pretty vague question, but if you give me any attributes of what is this going to be useful for, let me know. Yeah, what do you think? So DSP type stuff? Yeah, so what kind of, or is there any particular kind of DSP thing you're thinking of? Okay, so maybe like a Fourier transform and so on. Yeah, so those are reasonable things to try. This one has some limitations. Okay, so what this is useful for, given the way it's hooked up, is it's useful for what I'm going to call fine-grained ops or fine-grained operations. So by a fine-grained op, I mean this should Okay, this either has to finish in one clock cycle, because that's all that the ALU has, or it's going to stall the pipeline. Now, it's acceptable to stall the pipeline because these are not really complicated processors. If this was a really complicated out-of-order processor, then this could be doing something and the pipeline might not stall. But because we want to keep the soft processor relatively small so it doesn't take up too much of our FPGA, all the soft processors are relatively simple. So if this takes more than one cycle, it's going to stall the pipeline. It's not the end of the world, but it means our pipeline is not doing anything if this takes 100 cycles. So we're going to lose some of our throughput. Also, how many operands did it get? It's just hooked up to the regular operand broadcast buses. So a classic processor has 2 input operands to the execute stage, and it produces 1 output operand. This is basically hooked into those data paths. So that limits how much input you can get to it as well. So I can only send it kind of 2 pieces of data, and if it takes longer than the cycle, it stalls my pipeline. So it means it's mostly useful for things that kind of behave a lot like regular instructions, where they don't need that much input data, like add or multiply, and they don't take that long. But they can't be add or multiply because we can already do that here. So an example where this has been quite useful is things like cyclic redundancy checks. So cyclic redundancy checks you use in encryption, use them in parity checks. They're basically a whole bunch of shifts and XORs. So in encryption, basically all the encryption algorithms are based on like shifting and XORing things together so that you really mess up the bits. But they can be recovered if you know the key. A processor can do them because they are things like shifts and XORs and look up something in a little block of memory and so on. But they tend to be a lot of instructions because you're trying to XOR a lot and shift a lot to really scramble the bits. You can put that into hardware. You can make a custom hardware unit that for a certain encryption standard does exactly all the right XORs and shifts, and it does them in parallel or it pipelines it, et cetera. And it doesn't need much input. So the thing about encryption is you send in a little bit of input and you just smush it around a lot. Okay, so it actually fits this pretty well. Because the 2 limitations for this are ports. Okay, so it's limited by the register file. Okay, so normally in a simple processor like that, you just have 2 read ports to your register file, so you can read out 2 pieces of data every cycle. This then inherits that same limitation. And it also, as I said, it stalls the processor for long-running operations. Okay, so there are cases where that's useful, but these 2, it kind of limits you. Because you also want it to be a lot faster than regular instructions. So if you replaced, 2 regular instructions, it's not that much faster. You really would like to replace, 30 or 50 or 100 instructions, but except for things like some of these CRC algorithms, difficult to find something that needs 100 instructions that only took 2 operands, and that with hardware you could compute in quite a few cycles less. Okay, so that's one way you can hook this up. Another way you can hook them up is with coprocessors. Okay, so a coprocessor, you just have a microprocessor. So this could be a soft processor that you instantiated in the FPGA. Most FPGAs now also come with a limited number of hard processors. So usually they're ARM, and they have maybe 2 or 4 processors that are actually embedded in the chip. The reason they did that is to avoid that 10 times programmability overhead, because if most people want a small number of processors, you're better off to just build it right into the chip rather than program it out of the fabric. They could program it in the fabric, but again, they get a gain if most people are going to use it. So for either a soft processor or a hard processor, we can extend it using a coprocessor model, okay? So a coprocessor it's not as tied to the processor. This is really coupled. We actually hooked it into the processor pipeline. So it's very, very closely coupled to the processor. Coprocessor, we communicate over a standard bus. So two main ones are ECE, which is ARM's bus standard, which Xilinx uses, or Avalon, which Intel Altera made and use, although I think Intel is now also supporting ECE quite a bit too. So ECE is the most dominant of these, and Avalon is another important one. They work pretty similarly. So they're basically on-chip buses. You know, you send addresses and data, right? So you can say at this address, I want you to write this data. From this address, I want to read this data. So across this bus, this microprocessor and coprocessor can communicate. So they're not as closely coupled. It will take multiple cycles, for example, for the microprocessor to execute a read and to send something into a register in this coprocessor that might tell it go do something. And it'll take multiple cycles for this coprocessor to say, okay, here's some data that I'm going to write back to you, right? And I want to write it into maybe some registers you have, or write a status register saying I'm done. So the latency is higher than you had here. But we can do things now like directly connect this processor to memory. Okay, so this could be a bunch of on-chip memory on the FPGA. It could even be off-chip memory. We could hook it into a DDR controller so we can get an off-chip memory. So what this does is, well, we have a lot more flexibility. So it's not as closely tied together. There's higher latency between them. But we've broken this limitation of we're just getting a couple of operands every cycle. We can hook this coprocessor up to on-chip memory, off-chip memory, both, whatever we want. It's our choice. So we get more memory bandwidth. We can get more concurrency. Okay, so the processor sending a command to this coprocessor is just it writes to one or maybe a few registers. And then it just keeps going. It doesn't have to wait, right? And the coprocessor, when it's done, it could write back to a register that the processor can read, or more likely the processor just reads some status register, right? So this could interrupt the processor. Processor could read some status register. So there's no reason that one of them has to wait for the other. They can keep doing, they can do work independently and just synchronize whenever necessary by reading some registers. Okay, so whoops, it's more concurrency. So this is one with bigger potential. So people got very excited about this idea of custom instructions because it's very unique. But it turns out there are only a limited number of places where it's a win. Coprocessors, on the other hand, can be used all over the place. And so they have a bigger potential. And they don't operate in lockstep. Let's see. One other thing I should mention is when I'm talking about augmented processors here, I'm talking about you take a regular soft processor like a Neos or a RISC-V and you add some stuff to it. We're going to talk in a few lectures about what are called overlays, which are basically, usually there's some form of processor you put in an FPGA, but they are bizarre processors. Okay, so those ones are wildly modified so that they're still software programmable, but they're bizarre processors tailored to some application. And they can be quite efficient, but it's because they're so tailored to that application. Here I'm talking about kind of standard processors that you're modifying a bit with a custom instruction, or you're extending with a coprocessor. Does that make sense? Because processor is a very broad term, so you could say, well, yeah, that I'm being too disparaging of soft processors. The really customized ones can be very fast. But you'll see when we get to them that they are the weirdest processors you've ever seen. So, yeah. So for coprocessor, actually, so your example of like digital signal processing could be one, right? So let's say that I needed to do, like a big filter. Okay, so I want to do, or I think you said a fast Fourier transform. Okay, so I want to do a fast Fourier transform. So the microprocessor could basically write over this bus at memory address 100,000. There are 1 million data points, and I want you to do an FFT on them. And I want you to store the result, at address 2 million. So it only sent maybe 3 numbers across that bus. And the data already has to be in memory. Maybe it's on-chip memory, maybe it's off-chip. And now that coprocessor can just go, okay? And it can read that data from memory as fast as it can. So let's say it's on-chip memory. Then we might build a 1,000-bit wide bus between that coprocessor and the on-chip memory. And it could be, the coprocessor could be using the SIMD model, or just it's a big pipeline of hardware that's able to process like 1,000 elements every cycle. It could be extremely fast. Does that make sense? It might still take it like 2,000 clock cycles, but that's fine. When it's done, it'll interrupt the processor, or the processor will read over that same bus some status register and realize it's done. Does that make sense? So on the one hand, there's a little more communication overhead, because this one was like so tied in. There's like pretty much no communication overhead, but there's just way more flexibility. There's no way in this structure to get this thing, like 1 million numbers, and tell it to go off and do a fast Fourier transform of it. Does that make sense? Okay. Okay, so let me give you an example from a project that I was on where we made an augmented processor like this. Well, we didn't do it with custom instructions. We did it with a coprocessor. And it's kind of an interesting example, too. It also highlights how memory interfaces work a little bit, which is another important thing to, something you use a lot on FPGAs when you're doing hardware design. Okay, so the example I'm going to give you is a real one. It's called memory interface calibration. Okay, and it's possible that somebody from Intel works on this. So in that case, you keep me honest. See if I get anything wrong. So let me give you the context of what we're trying to do. So I've got a design. So this is on my FPGA. It's my secret sauce. It's my, that's my design that does something useful. My design wants to talk to off-chip memory. There are a lot of off-chip memory types. The most common one is double data rate RAM, or DDR. And there's like multiple generations of that, right? There's like DDR1, 2, 3, 4. I think 5 is now out too. Okay, so you don't want to go write all the low-level HDL and to talk to that memory interface. You just want to instantiate an IP core. And that IP core that you instantiate to talk to this off-chip memory has 2 pieces in it, something called the controller and something called the PHY. Okay, you may not see this. From your point of view, just like I instantiated an IP, but inside that IP there are 2 pieces. Okay, this is all on the FPGA. Okay, and then these are IOs of the FPGA. You go out over the circuit board and you talk to a bunch of memory chips. So what's called a bank of memory. Okay, the example I'm going to show you is for DDR3, but it's not much different if you were to say DDR4 or DDR5. They just kind of keep making the chips faster, but the protocol's not changing a whole lot. So for DDR3, the typical data rate here would be 1.6 gigabits per second, okay? And it's not 1 bit wide. These interfaces are usually about 64 bits wide. So every one of those 64 data lanes is transmitting data at 1.6 gigabits per second. The protocol they use, okay, it's called a source synchronous protocol. Who's heard of a source synchronous protocol? Do you know what that means in IOs? So if you don't, I'm going to explain it. That's good. That means you're getting value, so that's good. Okay, so there are basically 3 ways. Well, 3 ways that I can think of. Okay, so maybe somebody will come up with a 4th way I didn't think of. But three broad classes of protocols that people use for IOs to communicate between chips. At really low frequencies, you can basically use like a single clock on the motherboard. Okay, all the chips have the same clock. You send data on that clock. The other chip receives it at the next edge. You can only do that at very low speeds. Okay, so these are very simple interfaces that don't transmit very much. It's more, yeah, like really basic stuff, okay? As you go to higher speeds, you can't do that anymore because getting the clock to all the chips aligned with the data just proves impossible, right? You can't have a central clock that all the chips listen to and use to sample the data if they want to send data at high rates. So one of the two ways there's the really simple one. Then one of the two major protocols that you use to send data at higher rates is called source synchronous. Okay, so source synchronous, and that's what all these memory interfaces. DDR, GDDR is like graphics DDR. It's basically the same thing. RLDRAM is another variation on this, but they're all basically the same, and they're all source synchronous. So what does source synchronous mean? It means you send the clock with the data. There's no notion of there's like one clock that everybody's listening to now for these I/O transfers. You send a clock and you send some data with it, and you will use that clock to sample that data, okay? And this can be done at much, much higher rates because they're traveling just alongside each other, so there's not nearly as much skew. So for DDR, you send DQS. DQ stands for data. S stands for strobe. Strobe is just a clock that doesn't run all the time. It can start and stop. So to save power, if there's no data to transfer, they don't send this. There's no point in sending this strobe if nothing's happening. So it's like a clock, but it's a clock that stops when there's nothing interesting happening. So we call it a strobe. Then there's a DQ. DQ is 8 bits wide, okay? And the DQ is basically you basically align the edges of this DQS to the stable part of DQ. Okay, so you change your data bits away from the strobe edges. And the idea is to keep these DRAM chips cheap. The FPGA is responsible for sending this strobe, and the DRAM chip just takes this strobe and uses it to sample the incoming data for a write, okay? And it uses both edge. That's where the double data rate comes from. So it uses both the rising and the falling edge, and it'll sample the data. So to get the data reliably, it's important that the strobe is actually in the stable part of the data, which would be easy if this was a low frequency, but at 1.6 gigabits, so the distance between this edge and this edge is small. I'm thinking of what is 1 over 1.6 gigabits. That's like something like 600 picoseconds, right? And it's dropping, right? As you go to the next generation, it's gotten smaller still. So there's not a lot of time between these. I told you this was like 64 bits wide. So you send multiple DQSs and multiple DQs. For every 8 bits of data, you send a different strobe. The reason you send different strobes is there's skew between this data. If you try to send like one strobe for all 64 bits, it's not very reliable. At these speeds, there's just too much data skew. So you send one for every 8. Does that make sense? So we send a strobe to the memory. And this actually also happens in reverse, okay? So when we're doing a read from the memory sends back a strobe, and it sends the data, and the FPGA will use that strobe to sample the data. So it's called source synchronous, because whoever is sourcing the data doesn't just send the data, they send alongside it a strobe that you can use to capture it. Does that make sense? Okay, so the challenge is that basically, once you account for voltage fluctuations here, temperature variations, board mismatches on the signals, crosstalk, and DDR chips are made to be cheap. So their specs on their timing are actually pretty loose. Like these chips have variation in their transistor manufacturing. So they have like a window of how long it will take them to sample the data and so on. And those windows are pretty wide. So you basically have to adjust the edge of DQS and all of the delays on the DQs, like every single one of these 8. And then when you look at all 64, you got to do it across all 64 and all 8 strobes. Basically, you got to shift all their delays, okay? If you don't shift their delays around to account for all these mismatches, this will not work at this speed, okay? Like on no chips. It will work on 0 chips out of a million. So we need to adjust the delay of each signal. until the transfer is reliable. Okay, and the memory chips don't do this. It's the responsibility of whoever's talking to the memory, because this spec is made to keep memory chips cheap, which makes sense. You usually have a lot of memory chips and one processor or one FPGA talking to them. But it actually means that on both sides of this, if the FPGA is sending the data, it's its job to align the DQSs and the DQs so that the memory chip reads things reliably. And when the memory chip sends it back, it just sends the strobe less precisely aligned, and it's up to the FPGA to figure out how to shift things to make that work too. So all of the complexity is kind of on this side, right? This chip has an easier job. Okay, so all right, so does that make sense? Do people understand that? So as I said, this is one of the two major classes of high-speed interfaces. Does anybody know what is the other major class of high-speed interface? Which we'll actually talk about in brief as we go through some other blocks later on. What do you think? So this was source synchronous. There's another big category of I/O standards that are even higher speed, but they cost more circuitry and they have higher latency, which is why they're not the best fit at this point to RAM. Well, they have more bandwidth per pin, basically. So it's serial transfers. Okay, so serial transfers we'll talk about a little bit later on, but things like PCI Express, they basically don't have a strobe. They basically guarantee that you can recreate from the data a clock that you can use to sample. All right, and so which is even more tricky, which is why they take more area and they add more latency, but they get more bandwidth per pin. So if you're going to go a long way because your signal traces are expensive, they become the best choice at that point. For shorter traces where you can just have more wires and latency matters a lot, this is still the best choice, which is why memory uses it. Okay, so that's kind of the backstory. Okay, so let me get to the point. So the data path is actually 64 bits wide. Well, it's actually 64 bits of these DQs, and it's 8 bits of these DQSs, because we kind of bundle them, one DQS for every 8 DQs. So that's a reasonably wide data path. And the speed is fast. It's 1.6 gigabits per second at pins. Okay, we can't actually cycle the internals of the FPGA at 1.6 gigahertz. So there's basically some up conversion in the pins, like some time domain multiplexing where it takes in multiple inputs and basically serializes them really fast. So the last stage of hard logic at the pins up converts the data, okay? And the control, okay, so that's my data path. So my data path is going to have quite a bit of bandwidth, all right? So I'm going to need a pretty wide data path on the FPGA. And the control is complicated because, yeah, all of the complexity is on the FPGA to figure out how it shifts all of these DQ pins, how it shifts this strobe pin, how it should actually change that if it detects temperature is changing and so on. That's all on its problem. So control is this complex calibration algorithm. So basically when an FPGA or anything wakes up, let's just take an FPGA, it wakes up and you've got a DDR interface on the other side of the board and you want to use it. So you put this IP in that Intel or Xilinx gave you. And what it does is before your design gets programmed in, and before this controller will accept any commands from your design, it actually starts talking to the DDR. And it starts sending test reads and writes with all sorts of different timings. It's basically just shifting around these DQS and DQs, and it's seeing what comes back. And it's got a whole algorithm in there to try to figure out, well, what should I do next, right? How do I shift these till I get reliable communication? And these algorithms are highly proprietary. So every vendor of FPGAs and other chips, they don't tell people how this works, okay? They keep it pretty secret. And as new standards come out, like DDR4 and DDR5, the algorithms keep getting more and more complicated, okay? Okay, so the architecture that we chose for this, well, what do you think is a good architecture for this? For the programming models that we looked at recently. So this is a good match to a coprocessor because we actually need a lot of data. To actually read and write stuff to this memory, the bandwidth is high. If I take 64 bits times 1.6 gigabits per second, that's, what is that? That's 8. I think that's like something like 12.8 gigabytes per second. Okay, so that's a lot of data, right? So we use a coprocessor to talk to the memory because it's got to talk to it quickly, and you can't have basically a soft or a hard processor just can't handle those kind of data rates using instructions. But this control algorithm is really complicated. So it's useful to move a complicated algorithm to a processor. So we use the microprocessor plus coprocessor style. Okay, so what we did is took a soft processor, because you could have like 6 or 8 of these memory controllers in an FPGA design. Like you can actually have a lot of different DDR chips or other related I/O standards on the board. So you might need a lot of these. So not every FPGA has hard processors at all, and then they don't have enough, and maybe not in the right spot. So we use a Neos, which is a soft processor, and we use the small version of it, so it doesn't take that much area, but we can now put it down anywhere we want, right? If you need 8 interfaces, you'll get 8 of these. That speaks over a standard bus, which in this case was Avalon, but could be AXI. Talks to some on-chip RAM. So the on-chip RAM is just, RAM that the processor can access over this bus. And that same RAM can be accessed over this bus by a write coprocessor. Okay, so if there's a write command, basically the controller knows how to turn commands, and high-level commands like read from this memory address or write this memory address, into the low-level commands that DDR actually understands, because it actually wants to say here, activate this row, now write to this column, that kind of thing. So the controller does that. The PHY basically gets all the timing and signals exactly right. So this write coprocessor is responsible for getting all those timing and signals right. And the same thing for this read coprocessor. Okay, and then these go to these are both connected to the actual DDR3 pins, right? So they can actually directly talk to the off-chip memory, which is important because these two coprocessors can move much more data at a much higher rate than this Neos processor can. So it's not capable of talking to the memory at speed. Okay, so the coprocessors, they can handle those full 12.8 gigabyte transfers. Okay, so the way they did that is they ran at, so they run at, for example, 400 megahertz. Times 256 bits wide. Okay, so they can't run at 1.6 gigahertz, but can run at 400 megahertz. Send 4 bits, basically send 4 times as wide data word, and then a little bit of logic at the very end basically muxes that together, right? With the last stages being in the IOs themselves. So That's how you kind of match bandwidth here. I can't make this run fast enough, but I'll widen the data bus, and now it can send enough data. Okay, so the CPU, just basically by writing to registers inside of these read and write coprocessors and writing data into this on-chip memory, it can set up tests. Okay, so CPU sets up the tests. And these read and write coprocessors, stick the data back in this on-chip memory. So Neos processor might set up, here's a block of data in the on-chip memory, send to the write coprocessor. Okay, starting at this on-chip memory address, I want you to send to the off-chip DDR at this address 128 bytes of data. And it does it, and then the processor, and it'll write back the data that it reads. Well, then you can send a command to the read coprocessor saying, now read from those addresses and stick the result back here. And then the Neos can look at it, right? So maybe it wrote a whole bunch of 0 values, and then when it looks at what was read back, it actually got some 1s. So it'll try something, right? It can then send commands to these read and write coprocessors to adjust the edge timing and try again. And it's going to try a lot of things, okay? Because it's, and kind of analyze the results to try to figure out what to do next. Looking for how can I configure all of these edges and delays in order to get reliable communication. Okay, so it sets up tests, it analyzes pass-fail. And then it tries the next one, and so on. Okay, and this one is one where we have actually an example. DDR interfaces actually, in the last few years I was at Altera, had become a big problem. They were so hard for end users to get going that it was a big pain point. We also weren't keeping up with the latest memory standards, because there was DDR, but there are also a bunch of other related ones for SRAM and reduced latency DDR and so on. So you needed a lot of variations on these calibration algorithms, and you need them everything to just work. And it needs to work when the new memory comes out, not like 3 years later. So there was an older design, well, it was actively being worked on, but there's a design developed within the company already that was done using a different style, okay? And this had been worked on for years, and it was all hardware, okay? So it didn't use a soft processor. This project was moved to Toronto, and we switched to a soft processor plus coprocessor. So we actually have a kind of head-to-head comparison of two different styles. Okay, so this all hardware design had a state machine instead of a microprocessor to control this calibration. How big do you think that state machine was in terms of Verilog? There's no possible way you can know this answer, so don't worry, just take a guess, right? Like 5 lines, right? If it was 5 lines, probably I wouldn't do this. I wouldn't be telling you. But so any random guess of how big this is. And you can save Amin from being put on the spot if you just take a guess. So even if you don't know, you can just go, I don't know the answer, but I feel sorry for that Amin guy. I'm just going to take a guess so he doesn't get picked on again. So what do you think? Sorry? 1,000 lines? So who here has written a 1,000-line state machine in Verilog? Yeah, I'd hope not. I mean, that's going to be pretty painful to debug. So good guess. It was actually 20,000 lines of Verilog in the state machine. So 20,000 line Verilog state machine. And it still didn't have enough features. It wasn't keeping up with the latest standards. So you can imagine how hard that was to change. It actually had a larger area than the whole Neos processor. So this is an example of when your control starts getting complicated enough, hardware is worse than a processor. Processors store the control in instruction words. They become efficient for that case. So it was actually bigger than a microprocessor. It was so complicated, it was also becoming limiting in clock frequency. Because you can imagine it's got all sorts of loops in it, right? It's actually hard to pipeline. So it's difficult to keep fast, and it's also very hard to maintain. You can imagine how nasty that is. So yeah, this is an example where it's worked very well. And it was an example also where soft processor was good. We actually used the cheapest version of Neos. So this only took a few hundred logic elements, which is not much, because the Neos didn't have to be very fast. It could set up the tests relatively slowly. If it took 500 cycles instead of like 300 cycles, nobody cared. These two had to be really fast. And they had to be kind of weird, like able to do things like low-level adjust, talking to the IOs of the FPGA to adjust edges and stuff. This is kind of low-level hardware behavior. Okay, so anyway, so hopefully that highlights why it's sometimes a good idea to augment a processor rather than trying to do everything in hardware. But it's also a case where you couldn't possibly do this all in a processor. One more example where this kind of style can be useful, or where you can use soft processors, is what's called the slow path in packet processing. Okay, so FPGAs are used a lot in communications. They're used in a lot of high-end routers. They process packets mostly in hardware, so deep hardware pipelines, and they do it really fast. Okay, that's what you're selling. But there are some unusual packets. So most packets, look similar, but there are some packets that actually do things like reconfigure network links, rather than just say send this data to the following IP address. They can actually say, I need you to reconfigure some of your tables. Those don't happen nearly as often, okay? So it's not as important to be as fast on those, or they might have some kind of error condition in them. So for packet processing, you put most packets through hardware. Which is the fast path. Okay, so deeply pipelined, highly parallel. People have worked on it a lot. But some of these other weird packets, like management packets, are relatively infrequent. Okay, so management packets might be update your routing tables, exceptional packets like error conditions. So these ones, the slow path is often written in software. So the hardware just detects, oh, based on this pattern, this is actually one of those weird packets. Nobody coded that in my pipeline. Send it over the bus to a microprocessor, and it's going to process it. It might be 100 times slower than me, but as long as there aren't too many of these packets, it's fine. Okay? So you do the slow path in software. This is, even if you have maybe a 1/100th of the packets go through the slow path, that could still be too fast for a soft processor. So this can be one of the reasons that you put hard processors in an FPGA. It's not like the only reason, but it's like, well, I'd like to offload some things to software, some exceptional conditions, and a soft processor is not going to be fast enough. Or I need a whole bunch of soft processors. So for this case, you can use the hard processors that pretty much all FPGAs, or most FPGAs now have. And you usually don't have that many of those hard processors, so you might run out. And if you do, then I guess you'll wind up using the soft processors. But at least for most systems, they could handle this. And maybe I'll just say that. So this is where a hard processor on board or on the chip is useful. And the reason is you can make a more powerful processor architecture. You can clock it at 1 gigahertz instead of 300 or 400 megahertz. So it's going to get more done. And that same processor would clock slower if you put it in the fabric and have lower instructions, number of instructions completed per cycle. So you'll never get it quite as fast. Okay, third and final class of processors is vector microprocessor. Okay, which is just a microprocessor with SIMD. Okay, so that's used. It's a lot like having a processor controlling hardware units. It's just this could be a standard processor. So everybody know this term, vector microprocessor? I mean, all it means is a microprocessor with SIMD. So most high-end processors now, like x86 or ARM, also have some SIMD instructions where they can work on multiple pieces of data at once. You can build the same thing in an FPGA, right? Build a microprocessor, but don't have its instructions work on, add 2 registers together. Its instructions say add, 2 groups of 8 together, right? All of these 8 with all of these other 8. So that's a lot like the SIMD that we looked at before. It's just the whole thing is a processor. Yeah?
What is the difference between this and a GPU?
A GPU does use SIMD. So you can build a GPU on FPGAs, and people have done it. Again, I don't think this is an entirely rational thing to do because you can buy a hard GPU that is actually going to be a lot faster. Unless you are changing things. So where it does make sense sometimes is you take something that GPU is not good at. Okay, like unusual operations. It fits really well into some of the on-chip memory structures you could put in an FPGA, or it needs a lot of like special I/O. So there's some reason that it doesn't fit in a GPU. If you built a vector microprocessor and a really big one that looks just like an NVIDIA GPU, this is probably not an extremely rational thing to do because NVIDIA already did that without the extra layer of programmability, so you can just go buy it and it's going to be higher performance. Does that make sense? Let's see. So I guess the last thing, which I don't think I'm going to talk about, let me see. I'm going to see how far I could go here. Yeah, okay. I guess I will talk about the last couple of things, and then we'll do a few slides at the start of next lecture. Okay, so J. Okay, so these, I'm kind of gradually going from extremely common compute models. I mean, this one's still pretty common, but it's so similar to GPU that you do have to think about if this gets too similar, why am I doing it in an FPGA? So it's not uncommon, but you have to think about whether it makes sense in an FPGA. So another programming model is called cellular automata. Or okay, so this is kind of for physics computations. That's what this is really used for. And the idea here is you have a lot of physics computations are essentially on a grid. They're on a coordinate grid like this. Maybe this is like a little cube. And so these are all lattice points. They're all offset in 3 dimensions from each other by a little bit. And I don't just have one of these little cubes. I have like points like this through a whole big space defining essentially a discretization of some geometry, and I want to solve some physics equations on it. So for example, in electromagnetics, this you could basically say, okay, well, here's my electric field upward directed at these points, and based on how fast that's changing, my magnetic field x directed is going to be determined by how fast these y-directed electric fields are changing around it. So you can write that up as a big vector calculus problem. For any complicated geometry, you can't ever solve it analytically, so you discretize it. You basically say at all these points, we're going to say what all the fields are, and we can, using Maxwell's equations, we can actually write all the local update equations. And then we can simulate that in a computer. So what I just wrote down is basically an example of the finite difference time domain, which basically means discretized space and discretized time. We're going to step time forward in little increments, and we've got our electric and magnetic fields throughout the geometry in little increments. And we apply all of our calculus equations in local regions, and we record what happens, and we get the solution. And you can do this for all sorts of partial differential equations. So I'm doing electromagnetics because hopefully you all remember your electromagnetics. And I used to write electromagnetic field solvers, but this is done in every branch of engineering. For just mechanical engineers do this for fluid flow, for example, and shear forces in metals. So you can think of this. So this actually is kind of nice spatially because it is really modeling space. So you can think of this as data and operators. Okay, so data is like, what is my electric field at each point? What is my magnetic field at each point? And my operators are just going to operate on local bits of data and produce updates. Okay, so you can think of data and operators all being in a grid. So at points in some grid. So this actually kind of fits spatial computation very well. You're like, well, I actually have all these distributed quantities, and my updates actually only look at kind of nearest neighbors, because the magnetic field here is actually only a function of the electric fields right around it and how they change from one time step to the next. So it's it maps nicely to spatial communication. Okay, so let's say we implement this in space. So implement in space means we basically just take every one of those grid points and just say that certain logic elements in the FPGA are storing it and also producing the operators to update it. And we repeat that over the whole chip. If it's two-dimensional, it'll be really obvious how to map that. In 3D, we're going to have to, it's not going to be a perfect mapping, right? Like we can still distribute it in space, but clearly we have to kind of squish which grid points go where, so the communication won't be quite as local. But we could still have it work in space. So it's got a lot of nice features. It's like local communication. This is just a property of physics. If you look at all the partial differential equations, all the updates are based on local differences, like your neighbors. And the storage is also local, because we can just kind of store things in the part of the chip that's doing that part of the grid. And it's very fast. So if we can fit this whole grid in an FPGA, basically every few clock cycles, however many clock cycles it takes for us to do an update, we're basically at the next time step. And the way these equations work is you basically are seeing how the fields vary over time. So you start at t equals 0 with maybe a wave comes into your antenna, and you'd walk through what happens. You know, does it get reflected? What happens here? So it's really fast. There are some negatives. What do you think is the negative of this? There's a big negative, a big practicality constraint. What do you think? What do you think might happen if we implement this totally spatially? So we'll be fast, we'll be very efficient. What else? It could be. Sorry, I'm going to come closer. Sorry. So you're thinking the data dependencies might get you? Actually, data dependencies don't get you because it's all local. It turns out that your future values just depend on what happened 1 or 2 time steps ago, and on your local spatial neighbors. So your communication is actually local in time and space. As long as you wrote the old data out, like if somebody wants to look at the old data, you'll have to write it out. If they only care about the final answer, you don't even have to do that. Does that make sense? So locality is good. You actually don't get, the data dependencies are okay. But what happens is the physics simulations that you want to speed up tend to be big, right? That means they have big grids with thousands or tens of thousands or millions of points. So if you try to implement those, every point goes to a specific spot on the FPGA, it's extremely efficient, but also you just hit big problems just run out of space. You need an extremely big FPGA. So the negative is run out of hardware for large grids. So actually this same technique was actually used for FPGA placement by actually Andrew DeHaan, one of the authors of the Reconfigurable Computing textbook. He made an extremely fast placement engine because it just did local changes by looking at its neighbors and deciding, should I swap what is placed at this spot with what you have. But it needed a million lookup table, like a million LE FPGAs in order to, in hardware, solve the placement for a 2000 LE FPGA. So it was really fast, but he needed a really big FPGA that he'd actually placed and routed in order to solve the placement problem really fast for a small FPGA. So that's the problem with this. The biggest problems are what we care the most about. There is a tweak on it, though, that works better, which is called folded cellular autonoma. Folded cellular autonoma means instead of saying this piece of hardware represents this grid point and updates it, you say, I'm only fitting a piece of the grid in. Okay, so it's a local piece. I know I'm still going to communicate with my neighbors, but I'm only computing part of the grid. And after I've computed it, I have to send that to off-chip memory. And now I can keep the boundary data, maybe bring some other data that I stored before back in, and compute the next part of the grid. This works pretty well, still pretty fast, not as fast, but it can now do big grids. But it does now have more memory traffic, and it's not quite as fast. It is a lot like streaming. So this is like you're streaming parts of the grid, like parts of your physics problem, through hardware that represents a portion of the grid. And you have to keep doing that over and over again to do the whole grid. So it's related to streaming. And the textbook talks about it more. So I think that's all I'm going to say about that. But yeah, so there's some other interesting program models that come up in things like physics. And I think I'm slightly over time, so I'm going to stop there for today, and I'll be here in case you have any questions. So thanks.